Okay.
Start record. Okay.
Okay. Hi, professors. And our presentation today is about the electric vehicle sprouting problems with time windows and recharging stations. And our team members have three members: Jerry Phuong, Tyler, Shami, Brian. Next slide, please. And our presentation includes 6 parts: introduction, literature reviews, the electric vehicle sprouting problems with time windows and recharging stations. The next one is a hybrid VNS or TS solution method for the EVRPTW. The next one is numerical experiments. And the last one is conclusion. Next slide, please. Let's go to the introduction. Jimmy.
For the introduction of the paper is the issues addressing the increasing use of electric commercial vehicles or ECVs in urban logistics due to stricter environmental regulations and the push for green logistics. ECVs are seen as a sustainable solution due to their low emission and noise levels, especially beneficial in congested city environments. However, their limited driving range and the need for recharging pose significant challenges to traditional vehicle routing strategies. Next, please. Next slide, please. Okay. To overcome the issues, so the authors propose a new routing model, which is the electric vehicle routing problem with time windows and recharging stations, or shortened become EVRPTW. And this model extends classical vehicle routing problems by incorporating four things. First is battery constraint due to limited range. The second is recharging stations with variable recharging times. Third is vehicle capacity limitations. And the fourth is customer specific time windows. Next, please. Okay, so the main objective of ERPTW is to minimize the number of vehicles used and the total distance traveled. Due to its complexity, the author developed a hybrid meta-heuristic algorithm combining variable neighborhood search and taboo research to find high-quality solutions efficiently. Next, please.
And the next one is about literature reviews. Next slide, please. And for the literature reviews, we'll see there are three main points here. The operation research perspective. Sihi and Ashall and Ducker et al. Address the operation research perspective of green logistics and the integration of environmental issues into combinatorial optimization problems. Their work highlights the importance of considering environmental factors in logistic operations. And the second one is early models and their limitations. Goncalves et al. Consider a VRSP with pickup and delivery with a mixed fleet of electric and conventional vehicles. However, they do not incorporate the actual locations of recharging stations into their models. Contrast and frequency present the recharging VRSP, but assume a fixed recharging time. The last one is advancements in EVRPTW. And the EVRPTW problems go beyond earlier models by explicitly modeling recharging station locations, batteries level dependent charging times, vehicle load constraints, and customer time windows. This represents a significant advancement in the fields of green logistics and routing optimization. Next slide, please. Jimmy.
Okay. The part three is the explanation of EVRPTW. Next slide, please. So EVRPTW is a vehicle routing model designed for electric commercial vehicles, and in the research address limitation. For example, like first is reduced driving range, and the second is need for recharging, and the third is freight capacity limits, and the fourth is customer specific time windows. And this innovation, it supports green logistics and emission reduction strategies. Next, next slide, please. Okay, so for the model structure, first is defined on a complete directed graph, and for the nodes, there are customers, depot, and recharging stations with dummy copies for multiple visits, and routes start and end at the depot. And for the vehicles are first is homogeneous and also limited by freight capacity and battery capacity. And for the energy consumption alpha travel distance with rate hour h. Next, please. For the battery and recharging, so the vehicle consume charge while traveling. So while traveling, they consume energy or electricity, and the recharge of the vehicle is at the designated stations, and for the recharging, there's at a constant rate and also depends on battery level upon arrival. And for the model, the writer assumes that the speed is constant and there is no terrain effects and it's linear recharging for simplification. Next one. And for the objective and variables, so there is hierarchical objectives. So the first is to minimize number of vehicles, and the second is to minimize total distance traveled. And for the decision variables, it included xij, or the binary variable route from I to j, and ti, arrival time at vertex e, and UI remaining cargo at vertex I, and YI remaining battery level at vertex I. And this is expressed as a mixed integer linear program, or MLP. And as we can see in the slide, the constraints of the objectives, we can see it from the slides. Next, please. Next slide. Okay, so there are several constraints. So first is the constraint of route connectivity, and for the second constraint is for each customer is visited exactly once, and the third constraint is recharging stations, which can be visited at most once per route and cannot be more than once every route. And for the flow conservation constraint, the number of vehicles entering and leaving its node must be balanced. Next, next slide. And for the time window constraints, there are three. First is time visibility when moving between customer nodes. And then the constraints for arcs leaving recharging stations, recharging time depends on the battery level of the vehicle. And service start time must respect customer time windows. Next slide, please. And for the vehicle capacity constraints, we have the balance, which is cargo load, must be non-negative and not exceed vehicle's capacity. So there are two constraints that we can use here, and we can see for the constraint number 8 and also constraint number 9, uh, the cargo load cannot than 0 or equal or less than C, or the capacity. And for the battery constraint, first is battery level must remain within limits and account for distance traveled. And for when the vehicle is leaving the charging station, so it has a different or the other constraints, as we can see in the constraints number 11. And the last constraint is for the binary decisions, as we can see in the constraint number 12. Next slide, please.
Yeah, the next one is about hybrid VNS or TS solution method. Next slide, please. And we also found out that some meta heuristics of these articles, like variable neighborhood search, tuple search, and combining VNS and TS. And for variable neighborhood search, proposed by Malas-Danvix and Hassan, is an effective meta-heuristic for performing no-code search on increasingly larger neighborhoods. It has been successfully applied to various combinatorial optimization problems, including routing problems like VRPTW, and to effectively explore the solution space and avoid local optima. And the second one is about tuple search. It's a powerful meta-heuristic that guides local search heuristic to search the solution space economically and effectively. It uses a memory structure called the tuple needs to prevent cycling, starting from an initial solution. The best non-tuple move is conducted at each iteration. And the last one is about combining VNS and TS in every iteration. VNS performs a randomly perturbation move according to predefined neighborhood structures. The TS is run for a set number of iterations, and the perturbations move is added to the tuple list to prevent reversal. This combination leverages the strengths of both meta-heuristics to enhance search capability. Next slide, please. And next one is about the solution evaluation and acceptance. And for this one, include three parts: generalized cost function, simulated annealing criterion, and solution comparison mechanism. And for generalized cost function, which is to evaluate solutions including infeasible ones, a generalized cost function is defined. It includes total distance traveled, capacity violations penalty, time window violation penalty, priority charge violation penalty, and diversification penalty. This comprehensive function guides the optimization process. And the second one is simulated annealing criterion, which is to avoid getting trapped in no-go optima. SA allows occasional acceptance of worst solution. The acceptance is based on the cost of the new solution and a temperature parameter T that decreases over time. This promotes diversity in the in the search process. And the next one is the solution comparison mechanism, which is one of the best solutions found during the TS process, is compared to the initial solution. Instead of accepting only improving solutions, an acceptance criterion based on SA is used to further diversify the search. This mechanism ensures a dynamic and adaptive search process. Next slide, please. And next slide is a formula to evaluate solutions, including infeasible ones. The authors defines a generalized cost function, as you also can see on the screen. Next slide, please. And to avoid getting trapped in local optima, SA allows occasional acceptance of worst solution. And you also can see the formulas here with the Fs is the cost of solution, and the T is the temperature parameter that decreases over time. Next slide, please.
And the part 5 is numerical, the study. This part is about like evaluate the effectiveness of the our high risk meta heuristic algorithm that combine variable neighborhood search and taboo search in the shows the electric vehicle routing problem with the time window at recharge station. We decided to compare results with an exact solar IPM, ILOG, CBLES on the small side instead to the accuracy, analyze the contribute of the algorithm component on the large scale and the assist sensitivity uh, of the solution quality with the respect to the key problem parameter. The hardware in the paper they use is about Intel Core i5 750 with the 2.67 Hz memory for RAM and operating system Windows 7. The meta heuristic here in Java using a single thread configuration. The parameter tuning the methods, we adopt an adapting tuning strategy inspired by the method of the Brock and Singer. The algorithm include two main search phase. The first is feasibility phase 500 outer iteration multiple 100 taboo shot iteration and improvement phase 200 outer iteration multiple 100 taboo shot iteration. It about parameter work towards deterioration rates in the SA penalty coefficient for the capacity time window and battery constraint violation. Penalty update frequency and mass minimum tunnel for the taboo move diversification strength to the remote exploration and the percentage deviation in the total travel distance below 1% for all. The result from the table 3 and table 4 show the different parameter in fact the total distance travel. This the final parameter setting was selection based on the lowest deviation SA deterioration rate 0.08 penalty initiation 10 for all constraint penalty post mean is what 0.5 and mass is 5,000 penalty update factor 1.2 penalty update frequency every two iteration taboo shots 15 to 30 iteration, diversification factor 0.1.0, and taboo iteration per, per frame in 100. No parameter affect the number of the vehicle used, and the only observed was in total distance. We contracted benchmark dataset based on the Solomon well-known vehicle routine problem with the time window framework. The last is 56 instance each with 100 customer and 21 recharging station. The small is 36 instance with 5, 10 or 15 customer each. We use 6 instance time based on the customer distribution and time window configuration. The first one is random or, and second is C lottery, and third is RC mix. We have R1 C1 or C1 or 2 C2 or C2, and the energy constant in the instant design to reflect real battery limitation. One recharge station were laid at the depot, and 20 additional stations were random placed. Ensure each customer can reach with no more than 2 stations on way. Battery and energy. Battery capacity mass of the 60% of the average vehicle routine problem with the time window. Rule length or two multiple the length of the longest edge between customer and station. Energy consumption per distant unit 1.0 and recharge rate 1.0. Customer layout for the small instant were generated uniformly at random. The table 5 compare buffer between CBLES and high-risk mental heuristic on 36 small instance exactly matched with CBLES in the 32 out 36 case. Average is around minus 0.16% and runtime average of the 503 seconds. The CBLES hit the time limit without optimality rule in the several case. The collision algorithm achieved near optimal result in the fraction of the time. The table 6 evaluation component. In fact, through the 56 last instance, we find the full methods achieve the best performance. Remove the SA version performance and taboo shot along perform works. All the methods reduce same number of vehicle. In most case, collusion SA contribute to better result, and heuristic combination outperform similar variant. Table 7 compare our method again. Heuristic CCL and star of the art method TZK rose the 30 benchmark case. Our method found the best result in the 22 instance and average gap to the best node solution. Average runtime 27.07 minutes. Collusion. Our methods outperform legacy and advanced method on the multi-depot problems. The table A compare our method with the TZK on the larger instance, around 50 to 170 customers. TZK had the 0% average gap but requires 9.54 minutes. Our method found a better solution in the best case improvement and average case improvement. Runtime is 12.79 minutes, and collusion is our method is competitive and requires outperform previous benchmark even on the last dataset, And the table 9 perform on the RIN vehicle routine instead. Compare the uh, compare with the CBLES, saving the base heuristic and the luxury the base heuristic. Our method have the lowest average distance and in most cases were faster and some cases show over 1% improvement. Collusion is mental heuristic is accurate and efficient for the real vehicle routine with the recharge constant constraint. The table 10 invalue the algorithm on the last green vehicle routine instead compared with the another heuristic MCWS and DBCA. Our method produce the shortest distance in all case and in low more feasible customer average runtime in 198.58 minutes. Collusion despite the higher computational cost, the algorithm find the better solution. And the last table is compare the method to the best known pre-shot NBD method test on the 6 vehicle routine problem with the time window. Instant proof vehicle count mass with the best known pre-shot and the total distance slightly improved. The collusion method is high competitive even again with the lassable routine algorithm. The sensitivity set up to understand the algorithm robustness. We test 12 diverse benchmark case through the different labs, and each parameter was independently battery capacity, energy consumption rate, and the number of the recharge station. Battery capacity include the battery copper, reduce the pole vehicle count and distance. The improve the curve from the 80% to 100 and beyond 100 gains was smaller. The battery capacity is low to the optimal for the most instant and the consumption rate. Lower consumption rate improve feasibility, fewer detour, a higher rate in root cost, because more recharging, small effect on the energy feasibility and routine efficiency. The number of recharge station, more station lead to the better solution. Improve from the 10 to 15 station and gain from the 15 to 21, but slight improve in the runtime. The station placement is more practical than the quantity after a point. Collusion algorithm is high accuracy, strong robustness, excellent scalability, and ready for the real world application in the electricity vehicle delivery and routine. The real implementation, I use the Google Colab host on the Google servers to combine the Ruby in the Python and troubleshoot variable neighborhood chart and SA on supporting with GBU or TBU acceleration. And I try to show 3 results. The sample implementation. The first one is battery control EV routine. This log show the rule generated for the electricity behavior under the strict battery limitation without any charging station. The second is multi-depot EV routine, and we consider multiple depot and recharging station. Vehicle can start from the different location and recharge on the way. And the final is RIN VRP with the tabu shot. This showed a RIN logistics version of the problem incorporative emission data and using the tabu shot as a core optimization method. The conclusion we have this model called electricity vehicle routine problem with the time window at recharge station imperative limit the battery capacity of the electricity vehicle. Recharge during real world recharging time depend on the remind battery level. Strict delivery time window for customer and vehicle load capacity constraint. To solve this complex routine problem, we develop a high-risk mental heuristic algorithm combine two techniques, the tabu search and the variable neighborhood search. Together, these mental have the efficient cruise optimization for the electricity in the constrained logistic uh, environment. And our numerical experiment on the generate desk case demonstrate on the strong overall performance and the effective synergy between troubleshoot and variable neighborhood search lead to the high quality solution. Consistent research when test on the benchmark problem from the multi-depot routine, fuel-based routine, and elastical routine with the time window. The method show the support real-world decision for the fuel and the recharge learning able better adoption of the electricity delivery vehicle in the logistic industry and contribute to the sustainable and efficient urban transportation. This what we present as first step toward scalable and smart routine solution for the battery electricity delivery list, and the goal is to make the electricity city vehicle routine not just position but practical, efficient, and scalable for the future logistic operation. How? Thank you so much.